Section 4.3 is going to continue some of the things that we've started with logarithms. In particular, we're going to look at rules, or I like the word properties better. These are really properties of logarithms, things that are true about logarithms. And most of them hinge back on what we know to be true about exponents. So they'll feel quite similar in some ways to our exponential properties. As a reminder first, we've talked about the fact that logs and exponentials are inverse operations. We haven't actually seen this property, but it's a very good property for us to have. It tells us that when we have the base here and the base here matching, right, log base A of A, that these cancel one another out, and all I'm left with is the exponent x. And let me actually show you a justification for why that's true, because it's really easy to see. If we were to rewrite this using our scorpion tail, I would find out that the a that I circled on bottom raised to the x that's on the right-hand side is equal to a to the x, which is where it lands, and we would all say, yes, those are equal. They're exactly alike. So that's why it makes sense that the right-hand side would actually end up equaling x when I simplify this. But it's also true when I look at bases raised to a log. So you see this base a here, and you see the a as the base inside of here. And again, the a log base a will cancel and leave you with just x. But again, we could prove that using our scorpion tail if I were to draw the arrow all the way around. Remember, I would be changing it into a log expression, so the log base a, which is what I circled, going to the other side of x would equal the exponent where it landed, which is log base a of x. So using the properties that we've been using of being able to exchange exponentials for logarithms and vice versa, we can see very quickly why this has to be true. And the reason that this is so nice is because it simplifies our values, or our simplification for logarithms when it does happen to work. So for example, down here on a, it says log, and then it says 10y to the y plus 1. So what you'll want to remember, let me do this first, is that there's an understood base 10 here when it doesn't actually show up, right? It's a common log. So this has that property that we just mentioned above. This base 10 and this base 10, they match. So what it means is that I only have the exponent that will remain when I simplify this. This is simply equal to y plus 1. I don't have to rewrite anything, like in terms of with the scorpion tail stuff. I don't have to do any of that. I get it much more quickly when they happen to match. Do they match all the time? Well, no. But when they do match, it's very nice. And of course, the same thing's happening on the next one. I have a 7 here, and I have a log base 7 here. Those are inverse operations. So what will this part be equal? Don't overthink this. Yeah, 999. Okay, so when this property pops up, it's extremely clean and simple to use. Now there's a couple other properties, 3 in fact, that we want to take a look at. And what they are is they talk about how we can either combine or separate out logarithms. So the first one's called the product rule. So what you see is you see the log of a product, m times n. So if you see the log of two pieces that are being multiplied together, you can separate them into individual logs that are added. Log of m plus log of n. And the base can be anything you want. Okay, so base e, base 10, base 472, doesn't matter. I mean, obviously we do have some restrictions, but generally speaking, it's very broad. If multiplication inside of a log turns into addition, then it kind of should make sense that division inside of a log would turn into subtraction. And again, this is sort of hearkening back to what you think and remember about exponentials, right? Do you remember the corresponding exponential property here is a to the m times a to the n, and what it allows us to do is add m plus n like this. Do you remember that? right? That multiplication fact turned into an addition fact. And we had something similar here with subtraction a to the m minus a to the n, and it was related to division a to the m over a to the n. Okay, so this division-subtraction relationship, this addition-multiplication relationship exists just like they did with exponentials. Powers are a really interesting one, this number 4 one. The power rule actually says that if I have an exponent inside of the log like this, it can come down to the front. And you see that happen right here, x log base a of m. And if you think about why that would make sense, let's just do one that's pretty clean and straightforward. Let's say you had log base a of m squared. Well, m squared is m times m, right? And using property number 2 up there about the product rule means that I can separate them into addition. So this would be log base a of m plus log base a of m. And if you add two things together, that's the same as multiplying by 2 log base a of m. And there's nothing special about 2, it's just that it worked quickly for me to justify why that's happening. So anytime you have an exponent on what's inside of your log, the exponent can come to the front. Let me sort of remark on a few things that you don't have. You don't have anything that says what would happen if I had addition or subtraction inside of here, right? If it said log of m plus n or m minus n, you don't have a way to simplify that. That's not a thing, all right? And the same thing happened with exponentials. There's places where you can't simplify stuff. Okay, this is one of those places for logarithms. So what we're wanting to be able to do is use these properties both forwards and backwards, either to take something that's in this sort of condensed form like it is on the left and expand it out, or to take something that's expanded out and to recondense it. So we're going to work some problems from both directions to give you an example of what that looks like. So this is an example of what we would call condensing. The phrase that they're using on these directions specifically says as a single logarithm. Okay, so instead of it starting out the way it did on the left-hand side of these properties, it's starting out like it would be on the right-hand side of these properties. So this first one says that I'm adding some logs together. So which one of these 3 properties are we using? Sorry, say it again. The product, exactly. It's going to be the product rule. So we're starting with something that looks like this, and we're moving back to the left. So it says that if I have 2 logs, they have the same matching base, right? That I can condense this into a single log expression by multiplying the 2 individual pieces inside. So this means I can take and rewrite only one log base 3. And I would have x minus 1 multiplied by the x. Here's my x minus 1, and here's my x. It would be perfectly reasonable for you to leave it written like that if you wish. If you actually want to do the multiplication, that's fine too. We'll have other places where we'll need to potentially multiply in order to keep working the problem. This would be x squared minus x if you want to multiply them actually, like distribute them out. But either one would be okay in this context with these directions. What properties do you see present on part B? The 1/3 in front, what is that property going to use? Well, we are going to have the quotient, but not because of the 1/3. The power rule, okay? So we have a 1/3 in front, much like this x right down here is in front. That's going to be the power rule. We do have subtraction, though, as well, and that's going to be the quotient rule. Now, there's something that I need you to be aware of. The quotient rule only works when there's nothing in front of the logs, right? Or you could say there's an understood 1 in front of each of the logs. So in order to use the quotient rule, the first thing I'm going to have to do is to actually use the power rule. Does that make sense? So over here, the first thing I will do is use the power rule to pull these 1/3 up. There is one other way to do the problem. I'll show you that in a moment in case you're thinking, I thought of it a different way. So these are natural logs, so it's ln, and it's 6 to the 1/3 minus ln of 2 to the 1/3. Okay, so far so good? And then, because I have the subtraction, I'm able to combine them with division. So I have the natural log of 6, natural log of 6 to the 1/3 divided by 2 to the 1/3. Okay, we are definitely going to simplify the inside of that. They're just numbers. You can leave the power 1/3 if you wish. They both have a power 1/3, so you can understand that this is natural log, or understand this as 6 divided by 2 to the 1/3. And of course, 6 divided by 2 is 3. So you can either write this as 3 to the 1/3, or you could write this as the cube root of 3, because that's what the 1/3 power is. Okay, is that series of steps okay? Let me show you one other thing that you can do. This process will only work because they both happen to have the same coefficient in front, which they do. They both have a 1/3 in front. So you could pull the 1/3 out, like factor it out first, and rewrite this like this. Well, if they don't match, you can't do that, right? But they do both match. They're both 1/3. And then you could proceed with your order of operations. So the natural log of 6 over 2. So you have 1/3, the natural log of 3. And then you can pull the 1/3 up. So you'd have your natural log of 3 to the 1/3, or cube root of 3. Okay, in general, not a process that you can do every time. But again, if it happens to work on a particular problem, you certainly could do it that way. Okay, any questions on either of those before I swap slides? Okay. All right, rewrite as a single logarithm. Same directions as before, but there's far more mess going on. You see addition, you see subtraction, and you see... So again, I mentioned this on the previous problem, because you don't have all of them with a coefficient of 1. The first thing you have to deal with are the powers. All right, you have to get them all to have a 1 in front of them in order to use the product or the quotient rules. They have to have 1s. So my first step here will be to take anything that's got a coefficient and pull it up as an exponent, and there's a couple of them. So step 1 will be to rewrite the log 2 and the log x, and then I will have log of y to the 1/2 minus log of z cubed. Okay, that's the power property twice. Now, it can be a little bit confusing when you have multiple pieces of logs, like there's 4 logs here, right? I see addition, I see subtraction. I know addition turns into multiplication, I know subtraction turns into division, but what about the fact that sometimes maybe you have subtraction in a couple of places? Do I do a double division? What do I do? So the easiest way to think about it is that if it's addition, which it is in 3 places, right? The first 3 here happen to be addition, they go in the numerator. And if it's in subtraction, they go in the denominator. And it doesn't matter what order it occurs in, that always happens. So anytime you have logs that are added together, those insides of those logs will go in the numerator of a fraction. And anytime you have logs that are subtracted, those values will go in the denominator. So on this one, we have a single log. I have a 2 in the numerator. I have an x in the numerator, and I have a y to the 1/2 in the numerator. And then my z cubed is in the denominator. You can most certainly leave it like that if you wish. Another option, or if you're looking like in the back of the book for the ones that are odd or something like that, is that you might see it rewritten with a square root instead of a y to the 1/2. So either of those final versions would be quite reasonable. Okay? All All right, we're about to switch and go the other direction. So all of these are what we would call condensing or writing as a single log. Now we're going to expand or write as a sum and difference. So the directions, they say, write as a sum and difference of multiples of logarithms. So on part A, you notice that we have addition inside of the log. There's no way to fix that. That addition will stay addition. You can't separate into logs. None of that's possible, like I mentioned before. But the part that you can change is the fact that there's division, right? What will division turn into using properties of logs? Subtraction, exactly. So on this one, I'm going to have the natural log of what's on top, still a plus b. Cannot separate those guys. The addition cannot be separated. But the division will become subtraction of an additional, in this case, natural log, and that value in the denominator is an a. So I'm going to remind you one more time about another fact that we've seen before. Natural log is not a number. It's an operation. So it is not appropriate to somehow distribute that across. That's a no-no. It's not a number. There is no distribution property. We've seen this happen before with radicals, right, where we had the square root of a plus b, and we talked about the fact that we cannot distribute this so that there's a square root of a and a square root of b separately. Like, those are not the same. Exactly the same statement is true here. I cannot take a plus b and somehow do this sort of a distribution idea of natural log of a plus the natural log of b. That is not a thing. Okay? And we could do examples of numerical values to verify it if you wished to see that, just like we did with our radicals before. But you can't do that. That's actually a really nice fact because it means that you're done at this point. There's nothing else that you can do to expand or to rewrite this. Okay, on part B, we again have division. So we will still again be able to do this with subtraction. So this time it's log. It's a base 10, but you don't have to write it because they didn't either, right? Log. It's 3 to the negative x, and then it's divided by, so it's subtraction, the log of 4. Okay, is everybody okay with that step? There is one additional step, though. What is it? Yeah, there's an exponent this time. This exponent can come down to the front using the power property, right? The one here at the bottom. So I'll bring down my negative x. So it's negative x log of 3 minus log of 4. I'm quite certain on C that you see division again, right? But do you also see a place where there's some multiplication going on? What's being multiplied on C? What values are being multiplied? The denominator, right? The 2 and the y are being multiplied. Does everybody see that okay? These are two separate pieces using multiplication. Okay, so I'm going to show you the sort of shortcut idea, and then I'll show you why it works. I mentioned before that anytime you have pieces in the numerator, it's addition. Anytime you have pieces in the denominator, it's subtraction. Do y'all remember that? So I will have, this is log base 2, so we want to make sure our base matches log base 2. 5 is in the numerator, log base 2. 2 is in the denominator, and log base 2, y is in the denominator. And you'll see I put subtractions for the 2 because it's in the denominator and subtraction for the y because it's also in the denominator. Now, there's actually one more simplification step, but before I do it, I want to talk about why that makes sense when our property for logs before talked about how multiplication turned into addition, and now somehow I took multiplication and I made it subtraction. So let me justify why that works by taking this separately. I'm going to do each of these pieces individually. And if I did that, I would have log base 2 of 5 minus the log base 2 of 2y, right? whole denominator as a whole. The kicker is that this negative applies to everything that happens next. So while you might not think that it's necessary for me to do it, let me write it like this for the moment to make sure we recognize it as we use it. This is log base 2 of 5 minus, and then that property that says addition is log base 2 of 2 plus log base 2 of y. And do you see how this negative is going to distribute and apply to both logs? That's what's really happening there. And you can do it that way if it helps you to think about it. There's nothing wrong with it. But it will always work out that if you have multiplication and division, if it's on top, it's addition. If it's on bottom, it's subtraction. Okay? Does anyone see the one additional, I'm going to erase that last line because I need some more space. Does anyone see the one additional thing that I can do with how I've got my values currently written? It's not directly obvious. Yeah, good. This log base 2 of 2. Do you see how the bases match? That's that inverse property we did at the very beginning right here. It looks like this first one here. Kind of, right? The log base 2 and 2. The 2's are like where the a's are. But it doesn't really look like there's an exponent like the x is written on this a. What is the exponent on my 2 here? There's a 1. So this is a 1 up here. So it is necessary to simplify one more time. Log base 2 of 2 is actually the number 1. And you can rewrite this with it in whatever order you like, but there is a 1 showing up in the middle of this problem or at the end of this problem or at the beginning of this problem, wherever you put it, a negative 1 specifically. Okay, any questions? Yep, Anya? Where the brackets disappeared? The one that I erased just a moment ago. So they didn't disappear, the negative distributed through. So there was a negative in front of a log base 2 of 2y, like this. And there was still a negative here, and we wrote log base 2 of 2 plus log base 2 of y. Whoops, that was supposed to be y. And we talked about the fact that this negative distributed through, like this. And so when that happened, the parentheses went away. Yep. Sorry, I think I need a little more space on this slide. Any other questions? Okay. If you have your calculator, grab it out, because I'm about to show you a cool calculator trick. Should work for scientific calculators as well as for graphing calculators. You will need to be able to use your calculator on the tests. There is no way that you can do what I'm about to show you by hand. I mentioned earlier on, and I think it was one maybe that Hope had asked about from the last lesson, where I said it's written exactly the way it is, but right now you don't know how to find an approximation for it anyway. Do you remember that from earlier today? Okay. Well, what we're going to do now is what's called the change of base formula. And the change of base formula allows us to take something that's written in this form, log base a of m, which is an exact representation, and to make a ratio that our calculator can work with and understand. So the change of base formula says that the log base a of m is the same as the log, right, like the common log of m, divided by the common log of a. And it's actually true that you could do the natural log as well, the natural log of m divided by the natural log of a. So your calculator would be able to do either of those operations and to find a decimal approximation for the value you were working with. So if you're looking at part A and it says log base 3 of 4.78, I don't know why there's a period at the end of that. Probably just because I was thinking like end of sentence or something, I don't know. But it just should say log base 3 of 4.78. This property, this change of base property says I can rewrite this as either log or natural log of the 4.78 divided by the log of the base itself, which is 3. The reason that that's desirable is because your calculator can tolerate that because it has common logs, but it doesn't have the ability, most of them anyway, to change a base inside of it directly. So if you hit log 4.78, I would even press enter, and then divide by log 3 and press enter. Your calculator is going to spit back out at you an ugly number. I say it's ugly because it's irrational. It won't have any patterns or duplications or anything like that, but it'll give you a decimal approximation. We will use 4 decimal places. What value approximately does your calculator give you when you do this division? I saw several of you punching it in, so somebody. Yes, thank you. It's approximately 1.4240. So what that means is that you can actually check your work, right, on some of the ones that we were doing earlier if you wanted to make sure that the value you got actually worked in a particular problem. It also allows us to take a problem and solve it with a decimal approximation instead of leaving it in this exact form that feels sort of awkward. So if you're looking at part B here on this slide, if we take this and we rewrite it with a scorpion tail, right? So we write this as log, its base 0.23, cross to the other side of the equal sign of 18.4 equals x. That's how I'd rewrite it. This is solved and it's exact, right? I mean, there's nothing wrong with this answer per se, except that it feels awkward. It doesn't really look at, I mean, if you looked at this and you said, oh, my answer is log base 0.23 of 18.4, you probably aren't even thinking that that's a number. It doesn't look like numbers we normally work with, right? It still has an operation on it, this log. So you can take this and you can rewrite. In particular, you rewrite it as log of the value 18.4 divided by the log of your base, 0.23. And it will give you a decimal approximation, which we'll use to 4 decimal places. You might put a note to yourself somewhere on here that we're going to use 4 decimals. Okay, so what do you get for this log division? Did you do it, Cole? No? Did anybody put it in there? Good for you to practice while you're here. Is there any chance that it's negative? Okay. Yeah, I was like, negative is what I have written down. Negative, so we can have a negative come out of this too. Negative 1.9816. Okay, any questions on that? I have a couple more with the same idea, but they operate a little differently. C is written very much like B was. I take my base and I draw my scorpion tail around. So I rewrite this as log base 1.025 cross to the other side of the equal sign. So it's of 3 equals 12t. I need to solve it for t. What am I going to have to do that? Eventually. I'm not going to do it right now, but what am I eventually going to have to do? Divide it by 12, right? So let's rewrite this in our log expression that we've currently learned. This is log of 3 divided by the log of 1.025, and it equals 12t. We will eventually divide this by 12, but you might as well get your decimal approximation first and then do your division. So I don't actually have that step written down, so somebody's going to have to help me this time. What do I get, or what do you get, when you take log 3 divided by log of 1.025 with 4 decimals?
4.4915.
Okay, do I have a second on that? Did anybody else get that too? Okay, good. I've got several seconds. Good. All right, and then you can just from your calculator screen just hit divide by 12. That was an approximation there. Let me change that. So what do you get when you divide that by 12?
3.7076.
Okay, and are others getting that same value? Yeah, great. Simple enough. It's just that one extra step of division by 12 at the end. All right, D looks a little different. First of all, it's a log problem to start with instead of an exponential problem like B and C were. I can rewrite it with my properties of logs, right, like this, right, with a scorpion tail. So this is x raised to the power of 2.3 equals 12.33. That's the way we would rewrite it. But as you notice, that does not have a nice, it's not even got a fractional exponent. Like I can't change it into a radical, right? Like when I had like 1/3 and I was like, oh, look, it's cube root. Now I know how to solve it, so what do? So it's actually easier than you might imagine of what do I do. So what you're going to do is you're going to raise this to a power on each side. Let me move this down just a little. Oops. Try again. You're going to raise this to the power of 1 divided by 2.3. So on the left, what happens when you multiply 2.3 times 1 divided by 2.3? They cancel out. You get a 1, right? You multiply 2.3 times 1 divided by 2.3, you get 1. And your calculator can tolerate what's on the right just fine. The one caveat that I would mention is to make sure you put the new exponent you're using in parentheses. Some of your calculators will not understand you properly if you don't. They will think raise it to the power 1, then divide everything by 2.3. We don't want it doing that. We want the whole power to be 1 over 2.3. And as we, oops, I did that. I don't want those. What is the decimal approximation we get for this one? I don't have mine written out to 4 decimals. I don't know why. So does it have 2 zeros then, Cole?
0.7.
0.7.
Yep.
Okay. My calculator for later if I need it. Okay, did everybody's calculator do that properly, or did anybody's end up not giving them that value? I want to make sure your calculators are doing what you're expecting them to do before you leave. Yeah? Excellent. All right, that's the end of 4.3.